Welcome to lecture 7 of the Introduction to Computing course. As usual, we will start with a quick review of the previous lecture, and then I will continue talking about logic circuits, which we started talking about last time, and those were basically what we're going to refer to as combinational logic circuits. And then we'll introduce something called Boolean Algebra and Karnaugh Maps, which will be used to better understand the logic and also to be able to use to implement the circuits. And then we'll talk about something called sequential logic circuits. And we'll go on depending on time, the amount of time left. So in the last lecture, we started talking about the hexadecimal, which was a base 16 representation of binary numbers. In 2 nibbles make a byte, and each nibble is represented by a single character between 0 and F. We then spoke about why binary is important, and basically to be able to understand why everything is in binary, we had to go all the way down to the history of computing, and we saw how computers started using vacuum tubes, and then started using transistors. And the basic difference in the basic commonality between all of this is that both the vacuum tubes and transistors were essentially switches. And both the vacuum tube and the transistor were used to switch between on and off. And so essentially between binary signals. And the transistors were critical because they started using semiconductors, which could be miniaturized. And so as you started miniaturizing transistors, today you have trillions of transistors on a single chip, as you call it, that you see inside the hardware of a computer. And this continues to evolve. And we saw how transistors were basically operating, and they were essentially like a tap or a switch, which could turn electrical signals on and off. Okay, and once you are able to switch current basically on and off through a circuit, you can create something called a very simple circuit called a NOT circuit or NOT gate, which basically inverts the polarity of a signal. So if a signal is 0, it can turn it into 1, and vice versa. And how this can be done, we saw it through how a transistor is actually operationally implemented as an electrical circuit. And we saw some simple examples of how this electrical circuit operated. And once we understood this, we saw that you could create a whole bunch of different types of gates, not just a NOT gate, but AND gates, OR gates, and so on. And the Moore's law was something that Gordon Moore saw through his years in the industry and working as the CEO of the Intel Corporation. And he saw that because of the semiconductors' ability to be able to miniaturize, he saw that every 2 years, the density became double. And not only did the density double, but also Moore's law also said that the speed of circuits became doubled as well. So I'm only showing you the hard disk capacity, which is my personal experience over the last 2-3 decades. But you will also notice that similarly, the speed of electronic circuits also doubles. And so every couple of years, you see that your computer will have twice the speed in terms of megahertz or gigahertz, and so on. And this was an example of actual versus Moore's law's prediction, fairly close to each other. We saw how a microchip, we zoomed into a microchip and saw how that works. And these are the different gates that you could create. The simple NOT gate can also be used to make more complex gates. Essentially the same circuitry, but slightly more complex circuitry can be used to make AND gates, OR gates, and XOR gates. And then we saw how these gates can be used to perform logical operations. So for example, if you wanted to do a 2-bit addition, then you could use a circuitry to perform a 2-bit addition in which you would have a carryover and a sum. And today we'll go on to look at the slightly more complex example, which was a 3-bit addition, which I showed you last time, in which you have not just A and B being added together, but also a C term, okay? And we looked at this last time. So if I were to show this to you in a slightly better formatted way, this is how it would show in. So these are the three inputs, A, B, and C, and the outputs are the sum and the carry out or the carry over that we saw last time. And we saw that if all three of them are 0, both the sum and the carry over is 0. If all three of the inputs are 1, then clearly they should add up to a 1, 1. In which case, both the sum is a 1 and the carry over is a 1. This is, by the way, also referred to as a full adder. And the previous case, the 2-bit, this is also referred to as a half adder. Okay, a half adder. The reason being that there is, when this is carried over, the carry over needs to be carried over into the next addition. So you need to actually have a carry in, a C in bit over here to make it a full adder. And this can be combined together in what are referred to as a more complex operations, in which you can make multiple bit additions. Okay.
Network
network. We won't get into that. I think there is some background.
IBA के Wi-Fi भरोसा नहीं करना.
I'm going to mute all as usual. Not sure where that background keeps coming in from, but let's go on. So now, so hopefully, if you have understood this from the last lecture, let me introduce this term truth table. This is also referred to as a truth table. Okay, so the fact that certain inputs result in certain outputs, this is simply referred to as a truth table, and we'll refer to this as that in the future. Now, the question is that if we create a truth table, so this is something that we desire. Okay, this is something that we know that a 3-bit addition should result in a sum and a carry out, which should behave like this. But the question remains as to how do we actually determine the logic diagram for this. Okay, and by logic diagram, I am referring to this. So this is referred to as a logic diagram. Okay, and in the previous case, the logic diagram was fairly straightforward. Okay, and I remember that people actually volunteered and told me how the logic diagram will work. And we even, but we didn't really figure out how a logic diagram for a more complex case would work. So now let's try to understand that and see how we can actually create the logic diagram from this. Okay, so so any suggestions, any thoughts as to how we could actually create the logic diagram from this? So essentially, we need to have, how many inputs should we have? Clearly, there should be 3 inputs, A, B, and C. And these are all binary, so they're all zeros and ones. And how many outputs should we have? Clearly, there should be 2 outputs, sum and carry over or carry out. Okay, let's just call it a CO. So now the question is, how are we going to create the binary circuits, the logic gates, and the combination of all of that, which is called a logic diagram, based on this truth table? Any thoughts on that? And so I've sort of haven't been able to keep track of my initial recommendation that each one of the different sections would be given the chance to speak in each one of them. But I'll try to enforce that in the future. But today, let's just go on. And people can volunteer and just say your name and then answer. So how would we create the logic diagram from this truth table? Any thoughts?
Sir, Umar Ahmad here.
Umar.
Sir, first we will combine the 2 inputs together with a gate. It can be or AND gate or any other gate, and then the output of that gate to the input left, and the output of that gate pass through another gate, and then like this we can form a circuit and a logic diagram.
Right. So
by combining different outputs.
But basically what you're saying is that we'll start by combining things, right? So for example, you have 3 zeros over here, and you need to have a 0. For example, let's just focus on the sum, okay? Let's forget about the carrier over. So we need to create a logic circuit or logic diagram, which results in a certain set of ones. So it needs to be a 1 when C is 0, B is 0, and A is 1. It also needs to be a 1 when you have this combination. It also needs to be a 1 when you have this combination. And it also needs to be a 1 when you have this combination. So there are basically 4 cases, 1, 2, 3, 4, 4 instances of these. And how many combinations do we have here? 1, 2, 3, 4, 5, 6, 7, 8. You have 8 input possibilities. And why is it 8? It's basically 2 to the power 3 because we have 3 inputs, and each one of them can have 2 values. So that would result in a total combination of values of 2 to the power 3. If you had 4 inputs, it would be 2 to the power 4 different combinations, right? So there are 8 possible combinations of A, B, and C. And for each one of those, we are specifying what the output should be. So it's not that trivial. Earlier, it was kind of trivial because you could see that when you're forming this operation, if, for example, you wanted D, which was earlier defined to be the carryover, in the earlier case, we said that D is fairly straightforward. It's simply a combination of when both A and B are 1, we want the output to be a 1. So it simply
Sir,
was an AND gate. G.
Tariq Bal,
G,
uh,
Tariq.
answered that you put A and B in one XOR gate, and then you put the output of A and B and C in the second XOR gate. Is that what sum is?
Okay, so that's a good suggestion. So basically, what Tariq is suggesting is that we can have a specific solution. And what we could do is, just give me a second. What we could do is we could combine these. Just a second, I think yeah, okay. So we could use different techniques. For example, you're saying that we could use an XOR gate. Is that what you suggested? You're suggesting an XOR gate and
Yeah, two
another
XOR gates.
2 XOR or XOR gates, and we sort of
Yeah, first
combine
A and
these
B, and
A and B
exactly.
and take the output of this and combine this, and then what do we do?
And CN and the output of A and B.
Output of A and B goes to the second XOR, and then C goes here, and then what do we do?
I think that should be sum.
Okay, so you figured it out, but the question is, how did you do that? Okay, perhaps you've already come across this solution before, but if you can, Tariq, if you can explain, how did you actually get this?
I just kept on trying to put like two truth table values. I just like looked at the truth table, and I put A and B in the first XOR gate, and then I just like figured out from the truth table basically.
Okay, so what you're saying is sort of by trial and error, you were able to get it.
Exactly.
Okay, so that could work for a small circuit, but today, obviously, you can imagine that the combination of these circuits can be extremely complex. Okay, they could have literally dozens and dozens of inputs, and the output that we require could be extremely complex. Okay, if you can just imagine, if you're trying to make a computer and you want it to perform in a certain way depending on what your inputs are, so trial and error would not work. Okay, so we need to have, as I say, a method for the madness. Okay, so let's try to figure out if there is a methodology by which we can actually come up with this elegant solution that Tariq has actually suggested, which I haven't checked out, but it seems to be the right solution. Okay, so so the technique that we're going to use, there are a couple of terms that I'm going to introduce. And the first term that I'm going to introduce is called Boolean algebra. Okay, so this is a whole form of algebra, just like the algebra that you've studied. Boolean algebra basically deals with zeros and ones. Okay, so it's similar to your normal algebra, but it's quite different in the sense that all the values of the variables are simply, if you're saying x plus y, then both X and Y can only take on 0 and 1 values. And that's why you call it Boolean. The term Boolean simply refers to, as you know, in Python, we call it a Boolean term, Boolean variable, which simply means that it has two values, it's binary, okay? And the other thing that I'm going to introduce is something called Karnaugh maps, okay? So what you see over here on the left side is the Karnaugh maps. And you see, this is the Karnaugh map, okay? And the terms such as A, B, and A plus B, these are basically Boolean terms, okay? These are Boolean algebras that are using two variables. So let's try to understand both of these at the same time. We already know that this is an AND gate. So it can be shown as A star B, or A multiplied by B, or simply as AB, okay? That's a shorter term. So we'll refer to this as AB. So C is simply equal to AB, which is the AND gate. Now, when you're looking at a Karnaugh map, basically what you do is if you have two variables, two inputs, two A and B, you make a two-dimensional diagram, okay? On one side, you represent one of the variables, A, and on the other side, you represent the other variable, B, okay? And for each variable, you have obviously two possible values. They're binary, it's Boolean, so it can either have a 0 value or 1 value. And similarly, B can be either 0 or 1. Okay, so these are the inputs from the outside. The outputs are shown in the center. Okay, so this is the outputs. Now, basically, when you have an AND operation, clearly you only have an output of 1 when both A and B are equal to 1. Okay. For all other combinations, all the other three combinations, you have a 0. Okay, so this is how a Karnaugh map would be represented to indicate the operation C is equal to A and B. Okay. Similarly, if you think about the OR gate, which is A or B, so the outputs would be a 1 when either A is a 1 or when B is a 1. Okay, so you would have this, or when both of them are 1, so it would be a 1 in 3 of these possible output cases, and only a 0 if both A is a 0 and B is a 0. Okay. So now let's try to figure out can somebody tell me what would the XOR, the XOR gate, look like, the Karnaugh map for the XOR gate. So clearly it would still have A and B as the inputs. What would be the outputs in each one of these quadrants?
So Zarlesh,
These are Lish.
first block will be 0, then
Yeah.
1, and
Yeah.
then 1, and then 0.
Okay, very good. So this should be fairly straightforward. The reason why the only difference between the OR gate and the XOR gate is this term over here, that when both A and B are 1, then you want the output to be equal to 0. Okay. In other cases, it's going to be in both of these cases going to be a 1. So now, how do we represent that as a Boolean expression? So if we say C is equal to, we could simply show it as one of these terms. You could say A XOR B, but this is not really a Boolean expression. A Boolean expression is either something like A B or A plus B, or it could also have A bar B, something like that, or A B bar, and so on. Okay, so a bar represents. So if you say something like A bar B bar, this would refer to in the Karnaugh map as a 1 over here. In other words, it's going to be when A is a 0 and B is a 0, then both of these would become 1, and so the output would become 1. Okay, so I hope that's not too confusing, but and perhaps some of you have already come across a Boolean logic in the past. So can somebody tell me an expression for XOR using G Rayan? G, whoever it is.
A naught B plus B naught A.
Okay, so you can either refer to it as A naught B. Please turn off your mic. Yeah, so you can either refer to it as A naught B, or I call it as A bar B. Okay, this is different terminologies. But basically, it means that the output A bar B is going to be a 1 if A is 0 and B is a 1. Okay, then the output is going to be 0. It's going to be 1. So let's try to understand this expression that was was indicated. So A bar B is going to refer to, let me just redraw this. So A bar B, it is going to say that when A is 0 and B is a 1, we want the output to be equal to 1. Okay, this is what this term here indicates, A bar B. And A B bar is saying that when A is a 1 and B is a 0. Okay, so we want the output to be a 1 when either this term, this expression comes out to be true, or this expression is true. Okay, and that is why we have a plus in the middle. And we have a multiplication in between these two. Okay, so there's an and between these two, and or expression over here. So this is the only cases where the output is going to be a 1. In all other combinations which are not specified, the output is going to be a 0. Okay. So is that clear to everybody why this expression over here is equivalent, this Boolean expression over here is equivalent to the XOR, to the XOR operation? Any confusion about that?
Can you repeat this?
Okay, so let me just repeat it one more time. When you have a Boolean expression, it generally comprises of different terms, which can have addition in the middle. Okay, so you can have one expression, two expression, multiple expressions. Okay, now this Boolean expression will be true because there's an or plus in the middle. If this is true, or this is true, or this is true, it's going to be true when any one of these expressions is true. Okay, so in this case, it's going to be true when either this expression is true or this expression is true. Okay, now let's look at the individual expression. The first expression says A bar B. Now, when is A bar B going to be? What does A bar B represent? A bar B is going to be true when A is a 0, which means that A bar is a 1. Okay, and when B is a 1. Okay, so A bar B represents in the Karnaugh map, it represents when A is a 0 and B is a 1. Okay, so it represents this quadrant over here. So A bar B corresponds to this point in the Karnaugh map. A B bar represents this quadrant over here. Okay, this represents A B bar. Okay, so if this is still not clear, hopefully as we look at more examples, this will become clear. Okay, so basically what this is saying, G.
Why is there a circle on the
Name?
plus signs?
Name?
Tariq.
G Tariq.
Why are there circles on the plus signs?
Okay, so okay, so maybe I got that confused. There isn't supposed to be a circle over here. This circle over here is a special circle. Okay, now if you go back over here when we spoke about,
right?
that was an OR gate. So this operation over here is a special operation. It implies that this is an XOR operation. Okay, but normally, okay, and I circled this one over here by mistake when I was simply trying to emphasize it. Okay, so this is a normal plus. These are all normal pluses, which simply mean OR operation. This here is a special operation, which is an XOR operation. Okay, so I hope I haven't lost anybody so far. So now if you've understood the basic concept of a Boolean algebra and Karnaugh maps, let's try to see a more complex case. Okay, so this was this was simply what I've already shown you. Now, my next question is that let's take a look at this expression A plus B. Okay, now, okay, one of the things that I did not explain closely right now earlier was that when I refer to this term over here, this quadrant, I've circled it over here, and this refers to AB. Okay, this expression over here refers to A B bar and A bar B, as you've just discussed. Now A plus B can be thought of as a combination of either, if you look at A plus B, okay, A plus B refers to 3 quadrants over here, okay. This here term refers to A bar B. This term over here, sorry, that's A B bar, okay. This quadrant over here refers to A bar B, and this refers to A B, A and B, okay. And this 0 over here is a case of A bar B bar, okay. We're not going to talk about that because that's a 0. So essentially what we're saying is that A plus B can also be written as A B bar plus A bar B plus AB. Do people agree with that? Okay. Can you see that A plus B represents 3 cases, 3 input scenarios, where A is 0 and B, where A is a 1 and B is a 0, or where A is a 0 and B is a 1, or where both A and B are 1s. Okay, I hope that is clear. Now the question is that this is supposed to be equivalent to this expression. Okay, now what we're talking about is Boolean algebra, and I'm trying to show to you that how can you actually manipulate Boolean algebra, just like you can normally manipulate normal algebra. For example, you can have, if you say x is x times y plus z, this is equivalent to xy plus xz, and so on. Similarly, you can also have similar algebraic manipulation of Boolean terms. Okay, and without going into too much detail, this example sort of illustrates how Boolean algebra operates. Can somebody try to see how can we show that these 2 terms are equivalent? First of all, do people agree that these 2 terms are supposed to be the same? If so, why? And if not, why not? Can somebody explain that? Am I losing people, or is the question too difficult?
Just a minute.
Yes, sir.
So because both include A plus B and because of A plus B, they come in the
Sohaib, your voice is quite muffled. I'm not sure why. It's not very clear to me. Can you just speak up a little bit? Or if somebody else wants to volunteer. Yes, yeah. Why are these 2 expressions equivalent, Zia?
And A not B give you this OR gate, and AB is like the AND gate. So if you add both of their like outputs together, then it will give you the OR gate.
Okay, there's quite a lot of background noise in that, so I'm not sure if I quite followed. Let me try to just make sure that I'm clear in my question. Basically, what I've said is that A plus B, we've already seen that in the Karnaugh map. So I'm going between Boolean algebra and Karnaugh maps. Okay, in the Karnaugh map, you can see that A plus B is clearly represented by a 1 in 3 scenarios. Okay, a 1 over here, where either A is a 1 and B is a 0. And that can be expressed as A B bar. Okay, it's also a 1 when A is a 0 or B and B is a 1. That's represented by this expression over here, which is A bar B. Okay, and it's also 1 when both A and B are 1s. Okay, so this is the expression A and AB. Okay, so uh, three, three, three cases where this is the output is 1. Now this Boolean expression, this is a Boolean expression. Okay, this is supposed to be equal to A plus B. Okay, why? Because this is the simple expression, and this is sort of the broken up, more detailed version of that same expression. Now, in algebra, you can show at times, for example, these two expressions are equivalent. Okay, and we know that. So in Boolean algebra, we can also try to show that these two expressions are actually the same. So let me try to do that because this is a little tricky question. So the way I'm going to do it is I'm going to show you how in normal algebra you can make certain expressions. Similarly, in Boolean algebra, you can do similar things. Okay, but it's a little different. So what you can do
Sir,
for
Zarlesh.
Zarlesh.
Sir, are we supposed to use identities in this case? Like we can take A common and then B plus B naught, which is equals to
Absolutely.
1.
Absolutely, you can do that. So why don't you give it a try, Zarlesh?
Sir, we can take A common and then B plus B naught will be equals to 1.
Okay, excellent. So we basically,
And
what Zarlish is doing is combining these two expressions, if I'm not mistaken, and you're saying that A is common in both of these. So let's express this as A multiplied by B bar plus B. Okay, and the expression A bar B is left over. And I think, Zarlish, what you just said is that B bar plus B is equal to 1. Why? Because if you think about it in a Venn diagram as well, if you have B and B bar, if you combine B plus B bar, clearly you're saying either B or B bar, the inverse of B. Then obviously when you're doing an OR gate and you're combining these two, it has to be equal to 1. I think I don't need to elaborate on that. So this term sort of becomes similar. This reduces to A plus A bar B. Okay, and this is fairly straightforward logic. So we've almost got this term over here. Zarlish, is that what you were trying to say?
yes, sir.
Okay. Now take one more step and tell me how you can reduce this expression to simply A plus B.
I'm not really sure about it, but like I think it's an identity too. So like it will be A plus B, the direct answer.
Okay. Well, you sort of a bit of hand waving there. So yeah, this is not completely trivial. So we've made the expression smaller, but we've still got a problem. We're not able to show that it's exactly A plus B. Okay. So I'm going to do a little bit of a trick over here. What I'm going to show you is that this term over here, I'm going to remove some of this. Okay, so let's see if I can change this expression. I can write this expression as A B bar, okay, plus A bar B plus AB. And I'm going to write AB again, okay? Why are these two expressions the same? Because, in normal algebra, this would result in 2AB, right? But in Boolean algebra, if AB is true, then 2AB is also true. Okay, so you can reproduce this and it won't have any change on the result, simply because now we're only dealing with zeros and ones. It's only true or false. Okay, so I hope this is clear to everybody. Okay, if not, do let me know. And now what we're going to do is
Abdurrahman here.
G Abdurrahman.
bar and B bar can be also represented as A naught and B naught not gate.
Say that again, sorry. And anyway, let me go on. Okay, so what all I've done is I've expressed this term twice. Okay, and now I'm going to do what Zarlis just suggested, is that I'm going to take things common. So I'm going to take A B bar plus B. Okay, I've combined these two expressions. Okay, and now I'm going to combine these two expressions plus B A bar plus A. Okay, now do you see where I'm going with this? And so what's going to be the answer now? You can clearly see that B plus B bar is a 1, and so is A plus A bar equal to 1. So the answer is simply A plus B.
I have a question.
G name.
Nidal here, sir. How is A bar plus A equals 1?
Are
How
you
is A bar plus
okay?
A equals 1?
Nidal, are you in the auditorium right now?
No, sir, in the lab.
In the lab, and I'm just trying to understand this. The reason why there is positive feedback coming in is because the lab, because there's a speaker on in the lab that everybody is listening to.
One or two pieces, I guess.
Okay, because when you speak in the lab, then so okay. So basically, let me try why this happens so commonly and trying to figure this out. I'm going to mute everybody. And now, can you just open your mic and speak up?
Yeah, I just did. It's open now.
Yeah, but there's still a problem coming in because I don't know somehow. But anyway, go ahead.
Alright, so my question is, how is A plus A bar equals 1?
Okay, why is A plus A bar equal to 1? Okay, so if you think about the what we essentially doing is we're saying that when we're looking at A plus A bar, okay, so what are the possible values of A? A can either be a 0 or it can be a 1, right? So let's assume that A is a 0, in which case A bar is a 1, okay, because it's Boolean logic, so A bar simply means the inverse of A, okay? So we're saying 0 plus 1. So 0 plus 1 simply means either 0 or 1. So when if you go back to our the OR logic, the OR gate, we said that when either one of them is a 0, I had that earlier, I think. That was quite well back. So let's forget about referring to the earlier case. But basically what this implies is that a plus simply means that if either one of them is a 1, the output is going to be a 1. Okay. And so if A is a 0, then A bar is a 1, so the output is going to be a 1. If A is a 1, then A bar is going to be a 0. So 1 plus 0 is also going to be a 1. So in all possible scenarios, all possible inputs of A, the output of A plus A bar is always going to be a 1.
Yes, sir, I got it.
Okay. So similarly, B plus B bar is always going to be a 1. Okay. So I hope this simple example of Boolean algebra will help you be able to understand how you can manipulate Boolean algebraic expression and also use the Karnaugh map to be able to sort of understand what's going on. And now I'm going to take you through another example, and this will hopefully make things either clearer or more complicated. Okay, so this is simply what I've just written down. Now let's think about the 3-bit adder. Okay, now one of the students earlier mentioned that we could use 2 XOR gates to make a 3-bit adder. Okay, and he said that this was based on his experience, prior experience, and trial and error. Okay, so let's try to put a methodology to this solution. So what we're going to do is we're going to use a Karnaugh map. And now I've extended the Karnaugh map. So basically now what we have, if you have 2 inputs, A and B, the Karnaugh map is simply looks something like this. A can be 0, 1, B can be 0, 1, and so the possible combinations, you have 4 quadrants. Okay, but if you have 3 inputs, hopefully this should be clear to you that you will now have 8 possible combinations, 2 to the power 3. Okay, 1, 2, 3, 4, 5, 6, 7, 8. And these can be represented as follows. So we're going to do the label over here. So C can have 2 values, 0 and 1. B can have 2 values, 0 and 1. And A can have 2 values, 0 and 1. Okay. And if we arrange the inputs in this order, you will see that every possible combination is represented over here. So for example, this box over here represents the case where you have C is 0, B is a 0, and A is a 0. Okay. This box over here represents, this cell over here represents the case where C is a 1. Okay. And B is a 1, and A is a 0. Okay. So all possible combinations of inputs can be represented in this 2 by 4 Karnaugh map. Okay. So let's take a look at trying to be able to determine the sum, the value of sum in this Karnaugh map. So this is a little time consuming, but it's important to be able to understand the logic behind this. So let's take a look at the first cell. When all 3 of the inputs are 0, what is the output? That's clearly a 0. Okay. Let's take a look at this case. When it's 0, 0, 1, in other words, C is a 0, B is a 0, and A is a 1, which corresponds to this case over here. In that case, the output is a 1. Okay. This case over here represents 0, 1, 0. So that's 0, 1, and a 0. That represents a 1 over here. Okay. So there are 4 ones essentially. 1, 2. We've got 2 of those. Let's look at the third case. That's a 1, 0, 0. That should correspond to a 1, a 0, and a 0. So that should be a 1 over here. And the fourth case is all 3 of them are 1. So that's clearly a 1, and a 1, and a 1. So that's this case. Okay. So these are the 4 possible true cases, or one, or where the output is a 1, and the rest of them are clearly going to be zeros. Okay. So this represents the Karnaugh map for the output, which is referred to as a sum. Okay. Did everybody follow how I got this? Any question about this?
Yes, sir.
Okay, so this is clear.
And
So,
sir, which gate did you use?
okay, so I'm looking at the truth table, and I'm looking at the output sum. Okay, we'll also look at C out later, but let's look at sum. So the sum is going to be 1 in 4 cases. These 4 cases, right? In the rest of them, it's going to be a 0. So what we're going to do to be able to draw the Karnaugh map, we're going to look at those 4 scenarios, and we're going to put a 1 over there. Okay, so the first case was where C was a 0, B was a 0, and A was a 0. So that corresponds to this case. Why is that? Because here C is a 0, B is a 0, and A is a 1. Okay, so hopefully you can see that this box over here corresponds to this case. This cell over here corresponds to, let's see, I think corresponds to this case. Let's double check that. That corresponds to a 0, 1, 0. No, I think I got that wrong. Not this one. 0, 1, 0. This corresponds to this case, and so on. Okay. This clearly corresponds to all of them being 1. And this here corresponds to this particular case. Okay, so you can see that for every 1 in the output, we have a 1 in the Karnaugh map. Okay, and it corresponds to each one of the combinations of inputs. Okay, so I hope that is clear. Now, once you've created the Karnaugh map, what we can now do is create a logic diagram using this. Okay, and we can now represent the Boolean expression. I'm just going to remove some of these over here. Okay, and I can now represent this as follows. I can say that it's going to be a 1 when C and B are zeros. So it's going to be called a C bar, B bar, A. That's the first case when the output is going to be a 1. The second case that the output is going to be a 1 is C bar, B, and A bar. Okay. Can somebody tell me the third case? What's the third term in this expression going to be?
Tariq, C, B bar, and A bar.
Okay, very good. And what's the fourth term in this expression?
So A, B, and C.
Okay, I think that's Zerlish, A, B, and C. Okay, so I hope everybody got this. There are 4 terms in this expression, each one of them combined with a plus. And basically this is saying that the output is going to be a 1 when either this term is a 1, okay, which means that C bar, B bar, and A, which means that C is a 0, B is a 0, and A is a 1, or it's going to be a 1 when you have 0, 1, 0 as the input, and so on. Okay, so this essentially is a Boolean expression for the output sum. All right, so now we've gone from a truth table to a, well, we sort of haven't really used the Karnaugh map yet, but we can go directly from the truth table to a Boolean expression. The Karnaugh map so far is sort of helping us visualize this, but so far it hasn't really added a lot of value. Okay, but we'll see how it'll add value later on. And so we've gone to a Boolean expression. Okay. So this is the Boolean expression. And now, in order to convert this into a logical circuit, what should we do? How should we combine this into a logical circuit? Yeah, somebody. So how many inputs are there going to be and how many outputs? So we're simply looking at the single sum as the output. Okay, so clearly there's going to be 3 inputs, C, B, and A, and there's 1 output. And now we want to convert this expression into a logical diagram. So how would we do that?
There's Earlish.
These are like,
So we can follow the statement or the Boolean expression as in C bar, B bar, A. So like we will take C naught, then B naught, then A as 1, and then C, and then
what
B
are the,
naught, A
so
naught.
when you have a logic diagram, you need to have gates. Okay, so what gates are we going to use? Are we going to use
Still
an
not.
AND gate, NOT gate? Okay, so we're going to use a NOT gate over here. Let's say a NOT gate here.
And
Okay,
so for B2,
so we're going to use another NOT gate over here, and then A, and we're going to come. And then what are we going to do?
so it's multiplied, so we'll use an AND gate.
Okay, so we'll have an AND gate. So this is how the first term is
And
going to be
another.
coming up. And then we're going to have a similar, another AND gate, which will combine the other things. And there, so we've got 1, 2, 3, 4 AND gates corresponding to each one of these. And now we want to combine all of these into sum. So what do we need now?
So we'll combine all these AND gates using an OR gate.
Yeah, so we basically have We could have multiple OR gates, or we could just assume that this OR gate takes 4 inputs. Okay. So we could have something like this, which sort of is an overall picture of what the output would look like. So at the end, you're going to have an OR gate. Why? Because basically a sum of all of these, and each one of these expressions it's simply an AND gate because it's taking a multiplication of several inputs. So we can, I can simplify this expression as follows. C bar, B bar are going to be represented by this little bubble over here. And that's normally a quick way of showing that we're putting a NOT gate before that. Okay. So you've got 2 NOT gates over here, C bar, B bar, and then A. Okay, so that corresponds to this expression, C bar, B bar, and A. Okay, and we're going to take the output, put it into an OR gate, combine it with C, B bar, A. So this is C, B bar, A bar. Okay, and so on. Right, so C bar, B, A bar, and C, B, A. Is that clear to everybody? So I hope it's clear that how we've gone from a truth table to a Boolean expression, and then using that Boolean expression to create a logic diagram. Okay, any questions about this?
Sir, Babar here.
Ji, Babar.
Sir, how can we take 3 inputs?
How can we take 3? Okay, so I guess your question is, how can an AND gate have 3 inputs? Is that what your question is?
Yes, sir.
Okay, so actually this is sort of a more complex AND gate. This AND gate could actually correspond to a combination of 2 AND gates. Okay, I think we mentioned that earlier as well. So for example, you're looking at this expression A, B, and C. So what you could have is something like a C, B, and an A. And this is actually what it's doing. It's these 2 AND gates together are being used to represent a 3-input AND gate. Okay, so basically, when I'm representing more than 2 inputs, then it can be thought of as a combination of multiple gates together are being used to form a single expression. Okay, and similarly, this OR gate, a 4-input OR gate, can be thought of as 1, 2, and I think you'll probably need 3 OR gates. 1, 2, feeding in over here, third coming in here, fourth coming in here, and so this corresponds to 3 OR gates together forming this 4-input OR gate. So now the question is, why did we introduce the Karnaugh maps? Well, it did help us, hopefully, to visualize these particular scenarios. So as you can see over here, each one of these terms corresponds to an independent cell over here. Okay, but the Karnaugh map comes in when you try to simplify things. So for example, in some cases, you could see that here the expression C is equal to A plus B. The reason why it made sense and we didn't have to have the detailed expression is because what we did was we combined some of these cells. Okay, so basically, if you see here, I've got one red circle, which is combining these 2 cells together, and I have another circle which is combining these 2 cells together. Okay, and this one over here is in both of these. And the first circle over here, the first contour essentially expresses A, and the second one over here corresponds to B. Okay, so by combining A plus B, we have one term which is actually overlapping, but that simplifies the expression. Okay, so that indicates that you don't have to have the 3 separate terms separately added together. But what you can do is you can combine these two together, and you can combine these two together. Okay. And when you combine one of these two together, for example, if you combine these two together, this simply corresponds to a B. Okay. Right. So if you have a Karnaugh map like this, and you have these two terms over here, this is an A, 0, 1, and a 0, 1, and this is a B. So if you combine these two terms together, this simply corresponds to an A, okay, which is actually an A B bar plus A B, which as we know is simply A B bar plus B, and that comes out to be an A. Okay, so the Karnaugh maps helps us in combining these two terms together. Okay, and similarly, if you have another one over here, you can combine these two together, and that corresponds to a B. Okay, so now let's take a look at another example which will help us. In this particular example, the sum, each one of these cells was separate, so we couldn't combine any one of these. But I'll show you in the next example that you can combine some of these. So let's take a look at C out, carry out. Can somebody tell me what the expressions over here would be? Remember, we looked at all the terms which had a 1. Okay, so in this case, there are 4 ones again. So let's take a look at the simplest case. Okay, this corresponds to all of the 3 inputs being a 1. Okay, so that corresponds to clearly this cell over here. Okay, can somebody give me another solution for one of the other cells?
Tariq,
Tariq, which case are you
when
talking
C is
about?
0,
Yeah. B is 1 and A is 1.
C is 1 and A is 1.
Yeah, so let's take a look at that. C is a 0. C is 0 in these two cases. B is a 1 in this case.
Yes.
So now we've got these two. And then we talk about A is equal to 1. So it's clearly this case. So there has to be a 1 over here. Okay. So we've got that right. So this corresponds to, sorry, this corresponds to this case. This one here corresponds to this case. And okay, so I won't belabor this. So you can do the rest of it, and I'll show you what the result looks like. So you had a couple of the terms. If you fill out the rest of it, this is what the output will look like. Okay, so you'll have 4 ones corresponding to each one of these. Now earlier, you couldn't combine these, any one of these cells, because they were all sort of, separated. But in this case, you can see that you can combine some of these. Now let's try to combine these. So let's say that we combine these two together. Okay. So can somebody tell me the expression for these two when you combine these two together? Well, let me help you out. So in this case, we really don't care what, in both of these cases, B is a 1. So clearly this has a B. A is also 1. Okay. And we don't really care what C is. In both cases, C, this is a 1. So this corresponds to an AB. Okay. And in more detail, it actually corresponds to BA times C bar plus C. Okay. This corresponds to C bar, this corresponds to C. So you can see that by visualizing the Karnaugh map, you can actually combine cells together visually. Okay. So this is BA. Can somebody tell me the expression for, let's say, this term over here? I'm going to erase this one. Now, can somebody tell me the expression for this term here? Is that Shahir?
Yes.
G, go ahead.
C.
So it would be C And what else?
CB.
CB. Very good. So it's basically CB, and you're going to neglect A over here because A is either 1 or 0. Okay. Similarly, if you look at this expression over here, now I'm going to look at this term over here. These two can be combined together as well. So hopefully it shouldn't be too difficult to be able to figure out that in this case, it's going to be C and an A. Okay. And B, in both cases, B can have both values. Okay. So basically what we're saying is that this term, the CO, can be thought of as CA plus CB plus BA. Okay. So this is our Boolean expression. Now let's try to draw the logic diagram for this. Any suggestions for the logic diagram? So let's look at the output here first. Ji Zarlish.
So
Tariq,
there
sir.
will be 3 AND gates and 2 OR gates.
Okay, very good. So 3 AND gates and 2 OR gates. Okay, so we'll represent the 2 OR gates as a single OR gate with three inputs. Okay, so let's try to simplify that. It'll look something like this. And the first term will correspond to a C and an A. And the second term will be a C and a B. And the third term will be a and a B. Okay, so this will be an A and a B. So each one of the OR gates has got 2 inputs, and the output, the third gate, has a single, has 3 inputs. Okay, so hopefully it's clear how we got this. And in this case, what we've done is we've used the Karnaugh map to actually simplify the expression. Okay. And sort of it's a very important visual aid. You could have done without it as well, just churning out the Boolean expression, trying to simplify it, but the Karnaugh map simply helps us in visualizing it. Okay.
Nidal here.
G Nidal.
Is it the most simplified diagram that?
Okay, so that's a good question. Now, it is still not the most simplified. Okay, and if you go back to our original thought over here, somebody had suggested that you could actually use XOR gates to simplify things. Okay, and this was one of the suggestions earlier. Okay, so we haven't gotten to that yet, and let's see if we can ourselves, or should we just use one of the solutions given to us and try to see if it can be simplified. So now if you look at this case, this corresponds to 1, 2, 3, and possibly 4, 5. There are 5 gates being used over here. Okay, if you look at this, there are a total of 1, 2, 3, 4, 5, 6, 7, at least 7, and then several NOT gates, 7, 8, 9, 10, 11, 12, 13. So this probably has something of the order of 13 gates being used over here. Okay, and if you combine both of these expressions together, you have 13 plus 5, almost 20 gates, about 20 gates or so being used over here. Now, if you look at a solution, and I'll show you a solution, this is a representation of the actual solution that is used in the industry. Okay, so this has, as was earlier pointed out by one of your colleagues, it has 2 XOR gates. Okay, and it combines these, and it has 2 AND gates and 1 OR gate. So how many gates does it have? This can be thought of as a single gate. 1, 2, 3, 4, 5. A total of 5 gates, as opposed to what we were trying to do was about 20 gates. Okay, 13 plus 5, 18 gates or so. Okay, so this is clearly a much better solution. Now, let's try to see how they actually got it. Okay, and we can reverse engineer over here as well. And if we have more practice, we could actually get to this ourselves, but let's try to do a little bit of reverse engineering. Okay, so if you look at the carry out, okay, that's fairly straightforward. That we
Sir,
also had this. G, is there a question?
Sir Tariq,
Ji, Tariq.
can we use like this just
Can,
trial and error in the exams rather than the table method?
okay, so it depends on the question. So if I, in the exam, if I ask you to use Karnaugh maps and to go through a specific methodology, then I would be expecting that. Okay. If you don't, and if I'm just telling you, give me one solution, I don't care how you get it, then that's up to you. You could actually use trial and error. Okay, but it depends on what specifically the question would be in the exam.
Are we expected to learn both of them, or
Yes.
just the Karnaugh method?
So because the fact that I'm teaching you both the methods, I want you to learn them. Okay, because there are certain advantages. You may have only come across one of them earlier, and now there's a new technique. So it's good to learn both the techniques because they do have their additional values. Okay. So so let's take a look as to whether this particular expression actually makes sense. So if you look at the C out, that's fairly similar to what we had. We had an OR gate, okay, and then we have two AND gates. Well, they've and one of those AND gates is actually a combination of these. So let's see. Basically, this is saying that C out over here is a combination of A and B. Okay, so if you look over here, A and B is well. Let's take a look at this. Okay, let's take a look at S. So S basically is saying that two XOR gates combined together. Okay. Now, this is a little tricky, but if you get some experience, you can see that the XOR gate originally corresponding to this combination. Okay, it had a 1 in opposite quadrants. Okay, sort of like this. So this by this visual look can tell you that this corresponds to an XOR of A and B, XOR. Okay, however you pronounce it. So this term over here, a 1 over here and a 1 over here corresponds to, or this 1 and 1 over here corresponds to an XOR of A and B, of A and B. Okay, so this term over here corresponds to an XOR of A and B. Okay, and this term over here sort of represents this. And then what it's also doing is it's taking this and it's combining it with C. Okay, so we're running out of time, but try to look at this and try to sort of figure out how this would correspond to both of these Karnaugh maps. Okay, if you look at S, which was represented by this map over here, and C out, which was represented by this map over here. Okay, and hopefully you should be able to reach some of those expressions. So for example, this term over here corresponds to, well, let me show you part of the solution. If you look at this combination over here, it corresponds to A and B. Okay, so A and B over here, and this term over here corresponds to A, B. Okay, so that represents these two cells. Okay, and then these two over here can be seen to represent the XOR of A and B. Okay, so here's B, here's A, and these two terms over here are representing A, XOR of A and B. It's been multiplied by C. Why is that? Because C has to be a 1 in this case. Okay, so you can see that the term C out corresponds to AB, these two terms, and C, which is positive over here, multiplied by the XOR of A and B. Okay, so this is just one of the terms. And S, if you have more intuition about this, you should be able to figure out that that it corresponds to 2 XORs. Okay, series combination of 2 XORs.